So continuing with our playlist on calculus in a nutshell, we're going to start talking about functions of several variables. So today we're going to be talking about functions that may have the form f of x and y. So this is a function of two variables x and y. It's going to be equal to something like x squared plus y squared. So what this represents is essentially, this represents a function that is plotted on a three-dimensional space. So I'm going to draw three axes now. This is usually denoted as the x-axis, this is the y-axis, and this is the z-axis. And we have the origin here. So basically, when we plot a function of two variables, what is happening is for each point along on the xy plane, so you can imagine that this is the xy plane. For each point on it, so this would be some value x naught, this would be some value y naught, we're going to have a value of that is projected along the z-axis. So the z-axis is going to be essentially this. So this is the same as saying z equals to x squared plus y squared. So that's going to represent a point there. And if we continue with any generic function that is a function of two variables, you can imagine that we're going to start plotting points all around, and then we might create something that looks like a surface. We might create something that looks like a surface like this, and it is going to be continuous, just like a normal function. It is going to be continuous from minus infinity to infinity in all directions. And you can imagine that that surface is now going to be the function instead of just a curve, because if we draw the one-dimensional analogous, which we have been working with in the past few videos, we know that a curve is just a representation of a function in two dimensions. But that function is just a function of a single variable. So each point of that function is just a linear transformation, or just a transformation of those points of x along the horizontal axis. In this case, what we have here is the function of two variables is a transformation of all those points with respect to the xy plane. So you can imagine that this surface is sort of like a projection of that xy plane. And what do you think will happen when we have a function of three variables? Well, let's have a look at something like that. A function of three variables, which may be written as f of x, y, and z, is going to be a function of those three variables. So it can have any mixture of variables. It could have something like sine of zx plus 2y. So this is something that might be a function of three variables. Now we just talked about a function of two variables, the projection of the two-dimensional plane onto a third axis. So what is going to be this? How do we plot a function like this? Well, a function like this is going to be plotted as follows. So we're going to have our three-dimensional space. And now you can imagine that for each of those points, so we're going to choose a point in x, a point in y, and a point in z. So this is going to be a little more complicated, because now we have not just a plane but an entire space of points to choose from. So each of these points in this three-dimensional space is going to turn out to be a point in a four-dimensional space, really. And we cannot really draw that. We cannot visualize a fourth dimension because we are limited to our three dimensions. That's our conceptual understanding of the physical world. So how would we actually go about drawing a fourth dimension? Well, we cannot do that in here. So a function like this is not actually going to look like a surface. It's going to look more like a volume, because remember that we're now essentially working with an entire space of points rather than a plane. So it makes sense that our projection here is going to be a volume rather than a surface. So this concept is a little bit complicated to understand. And the thing about functions of several variables is that often we cannot plot them all at the same time, because remember, we're limited to a three-dimensional set of axes. So we cannot really plot functions of three variables or higher. We can only be limited by what we can deduce from such a system. So in general, so you can consider a system like this. Just to give you an example of what that might be like, imagine that you have a two-dimensional plane. So you have your xy plane, and now let's say we draw a circle. let's say we draw a circle. What is the function for a circle? The function of a circle is represented as x squared plus y squared equals to the radius squared. So this is going to have radius. And well, how do you plot this? Well, you just draw a circle like that. And you might argue, well, we can represent this as a function of a single variable if we just rearrange the terms like this, but no longer do you have a circle, you have now a semicircle, because you need to choose either a positive or negative sign. So this function is not the same as the circle, because you're not actually plotting the whole thing simultaneously. You're actually just choosing one of two functions to plot, and each of those functions is going to be a semicircle. So if you wanted to plot this, you notice that this will be in fact a function that is going to span that xy plane. It's actually going to pop out in some sense if you consider the radius to also be a function. So this is sort of the same notion as what a function like this would be. You would have a volume like this, but that doesn't mean you can express it explicitly in terms of a function of z, because remember, now we have 3 points, so 3 coordinates that we need to put into that function in order to calculate a value. So this gets more complicated when we deal with functions of several variables. So we may have a function of an infinite number of variables, and we often denote that by a vector x. So a vector x is going to be f of x1, x2, x3, and so on, up to a number xn. So we are going to have n number of variables, and each of those coordinates is going to be an input to that function. So we're going to see that we don't really need to know a lot about the geometrical meaning behind it, because obviously we cannot visualize it. It's beyond our reach. But what we can do is we can perform calculations, and we can apply operations to it. We can apply operators like the differential operator and the integral operator, and it will allow us to calculate all the things related to that particular system. So in general, in a physical sense, we're going to focus mainly on functions of 2 variables and 3 variables when we're talking about volumes, but functions of higher variables need to take on a whole new abstract concept. So we can no longer visualize them, because the space is just beyond what we can visualize. But just to give you an idea, this is what a function of several variables is, and you can see that the dimensions begin to expand just as that, and it's kind of like you're coming out of this plane. You're coming out of this plane into the z direction, and then this curve is actually becoming a surface. So it is no longer just a curve, but it is a surface that is continuous, and it just blankets over the xy plane like that, or it can actually be the other way around. It could be a function that goes like that, and there are endless possibilities. So in the next video, we're going to learn how to apply the concepts of the derivative to functions of several variables such as this one. So that's what we're going to cover in the next video.